chat box that's available. Just one little bit of housekeeping. There is a chat box that we will be monitoring. So if you have any questions, please let me know. All right, we might not respond to the question right away, but pose your question and we'll get to it at some point. All right, hope you enjoy.
Hey, hi everybody. My name is Clayton, and I have a little bit of a cough. So occasionally, if I seem like my voice is about to break out, it is. And I'll do my best to repeat myself and make sure you understand what I'm talking about. In this lab, we are working on enzyme catalysis. We're working on the actual breakdown of an enzyme. This is a pretty traditional lab. A lot of teachers will do this in your grade 12 biology course in some form, whether or not it's with potatoes. I'm going to be using livers. And it's one of those labs that can be really large, meaning that you could spend days on this. But ideally, you want to have the students take the learning from the class and look at an inquiry approach where they might ask a question and then analyze it, do some research, and hopefully solve the problem. So this particular lab, it would take place after the students have done some biochemistry, and they have they're probably going to go into metabolism and take a look at energy dynamics, and they know that enzymes facilitate that process. They understand that if the environment is not ideal, that the protein might denature, and a great model for showing protein denaturation is an enzyme, because the enzyme will no longer function. So what I'm going to do here is I'm going to demonstrate a more traditional approach of how I run this lab, and then how I change it up using the probeware. So that way you can look at the difference. The truth is, in my class, I run both. I run both the traditional gas collection tube, because the students can very clearly see the gas being produced. And then once they understand that gas is released as a product of the catalase enzyme breaking down the hydrogen peroxide, once they actually see that, then we move over to the probeware. The probeware, you don't necessarily see the gas being produced, but you see the results of it. As more gas is produced, the container that holds the gas is under more pressure. And so you can use a pressure probe to measure the difference. And that pressure probe graph is an excellent model to show the enzyme activity. Okay? So what I'm going to do is I'm going to first demonstrate from scratch, so from the beginning. So let's assume you're starting from the beginning, how I'd run this in the class, how I'd do the traditional approach, and then how I'd go to the probes. Okay? Now, I'm just going to move over to the table, this table here, and I hope that you can see what's going on in this table here. Okay, that's good. Now, you're not going to be able to see the table clearly because this table is a little higher than this, but that's okay, because I'm just going to do basically liver preparation. I don't know how many of you actually work with liver, eat liver. I would like to say I'm a fan, but it's been about 30 years since I've had my last dose of liver. So, take from that what you will. I don't usually use a knife this big, but I thought for this particular demonstration, I want to use big manipulative so you can see what I'm working with. Here I have some beef liver, depending on the experiment that you run. So what we do is we often have the students work in groups, and all the students will do the initial experiment first. If we do a second experiment, in the second experiment, I might actually have students, depending on how big the class is, work with different species of liver or different ages of liver. So a young liver, an older liver from beef, from cow, or chicken liver. They're very easy to find in the source. Now, when I'm doing the traditional approach, I actually have a higher concentration of catalase, so you can see the gas being produced. So what I'm going to do is I'm going to actually mix about 50 grams of liver into about 100 mils of water. So I have my balance, which you may or may not be able to see on the screen here. I have my liver on a cutting board. I have these whey oats, so I don't dirty my liver onto the balance. You can just use a brown paper towel, that's perfectly fine. It's a little cheaper. So I got this big giant piece of liver, and it's 47.7 grams. And for our purposes, that's good. I'm going to take my liver, I'm going to place it to about 100 mils of water. So the blender here. This is another crazy thing, right? In schools, since we opened the school, we purchased everything properly, the CSA approved and whatnot. This blender the price is silly, but it works really well. So it's a pulse blender, and we're just going to pulse it, so that way we don't add too much heat to the environment and cause premature denaturation. Okay? So I'm going to add 100 mils of water to this. I'm going to go off camera. I'm back on camera. So I'm going to add 100 mils. And I made sure, as I was preparing for this lab, that I cleaned these graduated cylinders previously. We use our graduated cylinders specifically for water, so nothing else goes in these. There's water. And I add my 47.7 grams of liver. I'm going to close that up. I have gloves on because the liver is really sticky, smelly, tacky. So I don't want it to affect the rest of my experiment. And now I'm just going to pulse out. I'm going to do that several times. In the classroom environment, I usually prepare this before class. I do that so that way there's a maximum amount of time in class to actually work on the experiment. I'll demonstrate the creation of this liver soup the day before or whatnot, so they can include that in their procedure. But this actual process here, I wouldn't normally do with the students. I normally do it before. Just before class, because if I let this liver sit for any amount of time, for the moment I start, blending it up like this, it's actually going to start to denature once it's outside the cell. Okay, so I didn't blend as long as I normally would. I'd normally blend this for probably another, probably 10 more bursts. But in the interest of our time, I have enough liquid in here to be able to do what we're going to do together. So now I've got my liver soup, my 50 grams of liver into 100 mils of water. This is pretty concentrated. I have it so concentrated, so you will be, smell that liver aroma, so that you will be able to see the production of the gas relatively quickly. I guess what we'll do is we'll put a copy of the lab up so that they can download it and they can use our recipe to pick up their lab in the future. But really, you want to experiment what the best figure means in your school. I'm going to take some of this and pour it in a beaker. Now, the thing about this, and the reason why I want to demonstrate this specifically, is I know some of my colleagues, when they do this, one of the big problems that happens is when you first do this, and you can't see it from where you are, but most likely, is you get a lot of, right, those bubbles up top. And you want those bubbles, you want to avoid those bubbles at all costs, right? Because what will happen is they'll cover the special filter paper we're going to use to run the experiment. We really just want the liquid. So I'm just going to pour slowly here. And this for the entire class, what I would do is I would then be trying to capture all this liver soup. But because it's just our demonstration, you and I together, we are just going to capture a little bit here. And once again, you see all those bubbles up the top? I don't know if you can see that very well. But all those bubbles, they're in the way. So if we can get rid of those bubbles, do something to get those bubbles out of the way, that would be ideal for us. The way I get rid of those bubbles is I just normally kind of scoop them off, right? So that way I have the liquid below. Another way to get rid of the bubbles is just to do a double pour. So in the second pour, the bubbles will normally come off the top. So once I have a liver extract like this, I need to put it on ice. So I have this bin here full of ice, and now I can use that for a little bit later. Now, This here is garbage because it's not on ice, so its activity is going down. I can't really use it. If you run this experiment over 2 days, you do want to be very specific with the amount of grams. But you know, the moment you have the same liver in the refrigerator after 24 hours, it's not going to have the same activity as it did on the previous day. So the students need to know that there's going to be some difference between the two. In the traditional approach, what's going to happen is we're going to react the liver extract, which contains the catalase, we're going to react it with hydrogen peroxide. And what's going to happen is we break down hydrogen peroxide into oxygen and water. And the oxygen gas is going to be something we can observe. So this is a gas collection tube, a giant test tube. And what I'm going to do is I'm going to fill this with water. I'm going to use this watch glass so I can flip it over, and I'm going to keep that in the water, and that's going to be my measurement tool to determine how much gas is being produced. So I already have this beaker full of just tap water. This does not need to be distilled water. It's an enormous amount of distilled water to kind of throw away like that. So I'm just going to pour it here. If you're the students, you probably want them to do over the sink. And I want it to go right to the top. So I'm just going to just overflow a bit, which is fine. I don't want that. I put my wash glass. I'm going to flip this over into this water reservoir. Now, I don't normally use a dissection lid as my water reservoir, but it's clear. So I thought if we had something clear, that would make it easier for you to see what's happening on the inside. So normally I'd use a different container. I'll show you what that looks like momentarily. Okay, so like I said, this is not the ProBware approach yet. I'm showing you the more traditional approach, and you can see how effective the ProBware would look. Okay, so I'm just going to open my burette clamp. It's weird, right? We call these burette clamps. So now I'm using it for kind of like a burette, but we also use this for everything but a burette. Put that down. So now you can see that my gas collection tube, the 100 ml gas collection tube, is completely full of water. When the students run it, they'll often, the first few times, they'll lose a bit of water at the top, and you just have to measure from wherever it starts. So it starts at 2, start measuring from 2. They don't have to redo it. A lot of times I forget to tell my students that initially, and then I come back 15 minutes later and they're still refilling. I don't know why. Down here, I don't know if you can see, but the gas collection tube is just below the surface of the water. And so this is my reaction vessel. So this is a little small ounce bottle here. It doesn't have to be amber, just what we have on stock in our department. And I have a 00 rubber stopper. And this is going to be my assembly. From here, I'm going to take a barrel pipette. This is a hold stopper. And I take my barrel pipette and I stick it in the hole. I'm going to take a pair of scissors. I'm just going to cut off the bulb. And so here's my reaction vessel. In this little container I have up here, I took some filter paper and I took a hole puncher and I punched it. Right? So regular filter paper looks just like this. I fold it up into halves and quarters, and I hole punched it. And so that gave me all these little discs. So I'm going to use these discs. And what I'm going to do, I'm going to tell you what the process is, and then I'm just going to do it. Because the moment I start and I take it off ice, it's not going to be as effective as I want it to be. So this reaction vessel, what's going to happen is I'm going to place 4 discs that I'm going to dip in the enzyme substrate, and I put them on the side of my bottle here. Because they're wet, in grade 12 biochem, we often talk about the adhesion, cohesion, capillary effect, all those sorts of things with water. So they should understand that when I take this wet filter paper, it's going to stick to the side of the glass. We don't want too much enzyme because it'll drip to the bottom. And why is that an issue? Well, once you have the enzyme discs, or the disc saturated with enzyme, stuck to the side of this bottle, I'm going to pour in hydrogen peroxide. And the hydrogen peroxide is going to be at the bottom, sitting here. And then when I have the hydrogen peroxide sitting here, my 10 mils or 6 mils or whatever I'm reacting, I'm then going to flip it and rotate it. And then the hydrogen peroxide will cover the discs that have the enzyme inside of them, and the reaction will start. And that's where where's my timer, they'll start at the timer. Here we go. Okay, so now you understand what I'm doing. I'm going to now, this is not ideal. Normally, when you have the setup, we'd have more ice around it, but for the purpose of this demo, I just have a little bit of ice below. I want my tweezers that I'm going to do for this experiment to be super fine, because you get some tweezers that are pretty dull. So this one is really fine. The filter paper, you want to make sure the students are taking a single sheet. They're taking a single sheet at a time, a single disc. So I dip this into my liver extract. I want to have the same person do it each time to try to be consistent. I'm going to put it through the neck, and then I'm going to put it on the side of my reaction vessel. So I'm going to do that 4 times, so 4 discs. 2. When the students are doing it, when I demonstrate, I make it look easier, but recognize the students are going to have some difficulty the first time. So if this is your first time running through it, you always want to allot just a bit more time, like with any experiment, just to make sure that you find out where the students are going to have problems. And this is one of the surprising areas. Students are not very coordinated, some of them, and you need some eye-hand coordination in order to pick up the discs, in order to put it in the bottle, in order to get the stick to the side. It's just amazing the ways that they figure out how to make things not work. So what I've done is I've taken my discs, I put them all on the side, so they're sitting there. If there's too much liquid on there, it will drip. So now I have this. I'm going to take this out, put this out of the way. That's going to leave this here. Now I get my hydrogen peroxide. So like I said, we'll upload the instructions so you have access to them. And for this experiment, for our purposes, I'm going to run it with 6 mils. A lot of students, when they're trying to be exact, they'll use our barrel pipettes, they'll stick it in the bottles, and they'll use a mil at a time. It's actually a little more accurate doing it like that if you're not practiced for it. So here's the hydrogen peroxide. I'm going to pour it in here. My reaction discs are on the top, so there's little chance of the reaction occurring, but there'll be some reaction. That's just experimental error. So I pour it in. I get my assembly that I created, turn it to get a seal, and now I'm going to put it so that the straw at the end of the barrel pipette is underneath my gas collection tube, and then I'm going to turn it, and then my partner would start the timer. And at that point, when the hydrogen peroxide is covering the discs, the reaction starts occurring. And so basically, every 30 seconds or so, they would record how much has been produced. So after 30 seconds, let's say 30 seconds has passed, my partner would look at this and say, oh, it's at 12. And then we go 30 seconds later, and you can see. So this, what it is a really good visual. We talk about the theory, we do, and here's a lab. If you jump right to the probe and you don't do this step, a lot of students don't actually understand what's going on. Here, the hydrogen peroxide, the liquid I put in, is being broken down by the catalase, producing water and a gas. Look, there's the gas bubbles. It's displacing water. Another 30 seconds, I'm at 26. And this gives a very good visual and a better understanding of the concept. So for our students, we have every single student, every single group, we call it the LowTech. It's the LowTech approach. So every single student does this. And so when they go to explain what's happening in their discussion, they're trying to interpret the data, they can visualize, okay, even though I have a black box that's magically producing some line, oh, this is what's happening. It's producing gas, it's under pressure, and thereby the increasing line represents this. So as tempting as it is to jump right to the probe, because the probe is going to make it much faster, it's going to give me really nice data. Doing the low-tech approach like this first is really advantageous. Okay, you get the, I don't need to run the spring water. You can see it's been running for what, a minute and a half or so. And look at the amount it's displaced. It's displaced 54 mils of gas. That's pretty impressive. This was actually more concentrated than what I normally do in the classroom, simply because I wanted to demonstrate to you how quickly this reaction can occur. So the next step they would do, they run that for like 5 minutes. They would take this out. They would have a partner in their group who set up the next reaction vessel with 3 discs. And with 3 discs, they'd notice that after 30 seconds, instead of 12 mils, it was like 10 mils. They'd do 2 discs. After 30 seconds, instead of 12 or 10 mils, it was like 6 mils. And so each time, they're getting a different volume of water being displaced. So that's a low-tech approach. So on day 2, what would happen is, now in the interest for us, so normally what I do is I actually make 2 different solutions. I make a day 1 solution, a low-tech solution that's much more concentrated because of the gas. And the day 2, I normally make it about 5 to 10 times less concentrated because we're dealing with a probe, a sensor that's able to measure very minute amount of pressure change. And if you use the pressure that I'm about to do in this experiment, so I'm going to do it. I'm going to keep the same gas pressure. It's going to be, let's call it an epic fail, probably in the classroom. Because what will happen is, as the students run the experiment with the HighTech, they're probably not going to recognize that it's going to blow and pop. And when that happens, they lose all the data and have to do it over again. But because I know what's going to happen, I'm only going to run the experiment for a short period of time, I can keep the same concentration. So I'm done with my water. Let's get rid of that. On the torch stand. And now we're ready for the HighTech. So for the HighTech, the reaction vessel is very similar, except instead of using this barrel pipette, I'm going to connect it directly to my probe. So let's get the software set up and ready to go. Can you see my software? So currently I have the SparkView open, and my understanding is you can see my desktop. I'm going to, so we have 2 types of pressure sensors here. I just want to pull them both out. I'm going to use the one that our students normally use because we don't have a class set of these, but we do have a class set of these. So what is these? This is an absolute pressure sensor. PASCO, in the older blue probes here, they have an absolute pressure sensor which measures higher pressure, and then they have a barometer pressure sensor which measures lower pressure. The other one I would use for, I actually did an experiment earlier today, you might see it in the background. There was a diffusion osmosis. We're looking at the movement of water across a membrane in a glucose solution versus a distilled water solution. So low pressure measures that. It's a really tiny change, or transpiration lab, where you have the water column changing. Perfect. Or for a lab like this, where there's going to be 52 or 54 mils of gas produced in 2 minutes, we want the big pressure sensor. So the absolute pressure sensor. We also have this wireless pressure sensor. And we could use this as well, but I only have 2 or 3 of these, and we have 8 of these. Because I have 8 of these, we're going to connect it to our Bluetooth, and this will allow it to talk wirelessly to our iPads or computers or whatnot. So I'm just going to turn it on. I am going to go to my screen here, so you can probably see my mouse moving around. I'm going to go to the big B symbol. And my computer is going to find number 819. So you got a class full of these, right? So it's great. They got the number on there. They can't miss it. It was a junior grade. Just be aware. They're going to do silly things like connect to somebody else apparently. But the seniors, they just want to get to the lab and get good results. So for the grade 12 class, you don't have to worry about that. So I'm going to click on my connecting to 819. It's connecting. Occasionally during our class, it asks us if we want to update our firmware. If you're in the middle of a lab with the students, tell them no, because they're going to waste 5 minutes waiting for that thing, that little bar to come across to update it. We just don't need that. So I'm going to hit cancel. I'm going to hit done. And momentarily on my screen, I'm going to get a bunch of units that are going to indicate that my pressure probe is connected. So there's my absolute pressure sensor. And I'm going to select that. By default, it's going to create a graph. And the default that it starts with is perfectly fine. It will change the axes to something that's appropriate for us a little bit later. So my probe is set. Okay, so that's the first step. The other step was water, my gas collection tube, the torque stand, big setup. This one, my probe. So let's do the same thing. I got a new reaction vessel, so I've cleaned that already, imagine that, and I'm going to get my filter paper. I'm going to get my extract. So remember, this is super concentrated stuff. So the graph that's going to be produced by this is going to be pretty dramatic. One disc. And trying to get them to be consistent. So normally if one student does the HighTech with the discs, get them to do them all. Unless they're, we find out later on that they're really completely uncoordinated, then it's okay to switch. Right? 2 discs. 3 discs. I find that some students, if I use this model here, they put their discs on the neck of the bottle, and they put it on the neck of the bottle. When they go to rotate the bottle, the hydrogen peroxide will not cover the discs, and therefore it won't react. So they need to make sure they get these discs into the body. Otherwise, you'll end up with some more errors. They want the discs as close to each other as possible as well. So I got my 4 discs in, and now I am going to take my 00 rubber stopper, and I'm going to take this, and I'm going to place it into that hole, right? This step here, it can be challenging. So we actually have cores for potato cores, apple cores, and we actually will core out this hole and make it a little bit bigger. You don't want it too big, so you need it to be a tight fit, because if you get gas leakage, then clearly the graph's not going to be a good representation. But I find just coring out a bit makes it a bit easier. And also the rubber stoppers, we want a nice conical, for us, nice conical one. Some rubber stoppers are cylindrical and they don't fit very well. So this is perfect. So I'm going to get my hydrogen peroxide. Same volume as last time. I did a bit too much, so let's get boil it off. I'm going to use a barrel pipette just to be a little more accurate. Okay, after this, I'm going to hit the play button and we're going to see the same thing happen. So I'm going to pour this into my reaction vessel. When you first pour it in, you might see a few bubbles. And that's okay. This means that I had a little bit too much catalase that tripped off my reaction disc. You don't see any bubbles, you know, did a really good job with the amount of catalase that was put on my disc. I'm going to seal this up, nice and tight. It's going to be under high pressure, so I know it's going to blow. Now, before I turn it over, my partner on the computer, they hit the play button. And then typically what I do is, like at 10 seconds, I'd say flip it, just so it's consistent. So 7, 8, 9, 10. So I'm going to flip it here, and it's going to start reacting. Now look at that graph. Look, it's gone. It's up. It's astronomical, right? I can feel the pressure already. So remember, what just happened? In 2 minutes, that previous example produced 54 mils of gas. So can you imagine 54 mils of gas fitting into this little tiny brown tube or into the clear plastic tube that leads to the pressure sensor? You know it's not going to work out. You know it's going to pop. No matter how much I hold it, there's going to be some kind of leakage. So if you want to avoid the epic fail, then what you want to do is, if you're running an experiment like this, just test it. Because different livers on different days from different stores, they have different concentrations. And I found that out the hard way as well. One day, so the recipe ingredient of 25 grams and 100 mils was perfect. And the next day, it was too weak. And the other day, or next year, or semester, it was too strong. So your best bet, that's what I do before class in the morning, is I'll just test. And I'll find out what is a good gram concentration for the liver that I currently have. And then I share that with my colleagues, or I actually just make up one for all of us, stick it in the fridge, and then we use it. You also want to make this up just before the experiment, as close as possible, for the reason we talked about before. Even now, this is bad technique I'm doing here. I got my liver, see my little tiny bit of ice. It's, it's denaturing right in front of my eyes. But for our purposes, we know that it's a mistake. So we'll just keep on working where we are. I assume you can see my graph on my screen. Yeah. So if you can see my graph, look at that pressure. So see that curve? So I'm going to let that run until 120 seconds. If I'm doing the gas collection tube, you really want to run this for 5 minutes, collecting information every 30 seconds, maybe every 20 seconds. But 30 seconds is about right before they start to get confused and do some errors in the number, recording the numbers. But here, 120 seconds, that's plenty. Run this for 2-3 minutes, and I'm done. So I'm just going to let go. You're going to hear a... So that's what happens to a lot of students. They don't hold it tightly enough, and then the whole thing blows. So I ran it for 120 seconds. I'm going to hit stop. So now I can see that curve. That's my curve with 4 discs. So I can now do this same experiment. How long did that take? The setup was a minute, minute and a half, and the running experiment was 2 minutes. It's taking a bit longer because I'm waving my hands around the air. But if you actually run the experiment, that whole process, 5 minutes, tops. Now I'm going to do the same experiment with 3 discs, 2 discs, 1 disc. What am I altering? I'm altering the amount of enzyme. And if I'm altering the amount of enzyme, I should see a change in my graph. Okay, so let's try that. Look at that, another new bottle, magically clean. So because I'm not going to do 4, 3, 2, and 1, let me just go from 4 discs to 2 discs. Okay? When you deal with the filter paper, you want to tell the students as much as possible not to handle it with their hands. They've got oils and creams and all sorts of things that are going to impact the experiment. You want to do everything you can to have to keep the variables as tight and controlled as possible. Second disc. Okay. When I use this software, when I hit the play button for a second time, it's going to just produce a new color, a new graph is going to be superimposed. So not a lot of work on my hand. I'm going to take my 6 mils of hydrogen peroxide. And the last time, first time was perfect. Second time, I overpoured. Let's see what happens this time. Oh, perfect again, yes, all right. So I have my 6 mils of hydrogen peroxide. I'm going to pour it in. I'm going to seal. I hit the play button, and at 10 seconds, approximately 10 seconds, I'm going to, if I have a partner, it'd be exact. Right now I'm kind of by myself, so I'm kind of missing that, that 10 second mark. I'm going to hit play. And right when I get to the 10 seconds, I'm going to flip it again. Almost there, and now I'm going to flip. Hold it. Okay, so this is with 2 discs. Look at my graph. There's no question about what's happening. You can immediately see the relationship between the graph. I don't have a good grip on this. I might blow before. I have an immediate relationship between the number of discs and my graph. Look at the pressure. The pressure is dramatically reduced. So now, when you're talking to students, even though you produce this graph, I mean, as a bio teacher, I want my kids to be able to take the numbers and create their own graph. So I can export the data. And actually, that's what we have them do. This program allows us to export the data, import into Excel, and then use Excel's graphing process. We get them to do a line of best fit. We get them to compare the slope, right? All that stuff they learned from their math class. And we get them to make a relationship between the number of discs and the rate of activity. So what does this tell us? Well, this is not anything to do with denaturation, right? We're talking about kinetic molecular theory or particle theory. We're talking about the idea that there's more enzymes and more active sites, and so therefore there's, in the purple line, the first experiment, there's more catalysis occurring, and in the second one, there's less active sites, so there's less catalysis occurring. So they can make that interpretation from this data. And the great thing is look how long this took. If I wasn't talking and doing all this prep and whatnot, I could do 4, 3, 2, 1 realistically in about 15 to 20 minutes. And I could spend the rest of the time doing the analysis. If I use the traditional technique, my data, first off, you have to make sure they're reading the meniscus properly, and they'll have to convert the milliliters of gas into something that's more interpretive, like this pressure, and they could do a good job, but it's a lot more work, and it's not nearly as accurate, and it takes far longer, and they're spending the entire lab measuring, refilling, and so on and so on. So I've hit the 2-minute mark, so I'm gonna let this go. And hit stop. And so you can see what's happening here, right? So I'm gonna do another experiment here. It's the same style here. So this one is looking at the number of discs. And so I talked about in the blurb about making inferences about protein function based on gas activity. So to do that, in addition to the active sites in these discs, let's bring in something that might denature. So with my class, typically we do the traditional techniques, so they see the mechanism. Then we do the probeware, and we divide that into various parts. And one of the parts, the students are looking at different number of discs to represent them different concentration, different amounts of enzyme. Another one, they might use a different amount of hydrogen peroxide. Another one, they might actually have temperatures. So we have a constant temperature water bath, but you can just set it up on a hot plate and get 4 degrees from the fridge, room temperature 21, set up water baths at 30, 40, whatever you'd like. You can't go too hot, right? Because you want them to hold it in the water. Really, anything above 45 is really uncomfortable for the hands. And then you ask a really good question. You want the environment to be at 40 degrees, or you just want the substrate to be at 40 degrees, or you want the enzyme heated to 40 degrees. There's 3 different ways of looking at it. And it leads to very good questions that you want the students to ask. You can also do metal salts as a denaturation process, and that's the one I'm going to do because it's the easiest one for me to demonstrate. Or you can do ionic salts to see if that has a difference. You can do species, you can do pH. So pH is great. Why? Because a lot of students make the assumption that at neutral pH, things work really well, because that's what we teach them. But what about an enzyme that's supposed to work in the stomach? Is that going to be a neutral pH? Is that going to be an acidic pH? Is that going to be a basic pH? I don't know. I do know, but we don't know. That's something they have to determine. So if you want to do a pH lab, I know when I do pH labs, as a biologist, I don't want to look at all the recipes and construct this whole chart that allows me to create a pH of 2. I just spend a little bit more, and I buy these little tablets, and I put these tablets. We have one for every single pH. I put one of these tablets here into 100 mils of water. You'll probably see these, and that will give me my pH of 4, or my pH of 6, or my pH of 10. So I find these really handy. And so on those, I've made up my pH solutions. I have silver nitrate, copper sulfate. So here are 2 metals. And a question that we might ask the students going beyond the curriculum, going beyond the actual content that we teach, is we know that some metals are very toxic, right? So what is it about it? What is it toxic? Is it more toxic? How can we determine it's more toxic? Well, let's say we experiment with 0.1 molar of copper sulfate and 0.1 molar of silver nitrate. And we find that one has a little bit of activity and one has absolutely none. From there, they should be able to infer which one's more toxic, assuming that everything else is controlled. So I'm going to take my silver nitrate here, and I'm going to run the same experiment. I'm going on camera. And I got another bottle. Okay. So I'm going to take my discs. I need 4. If I could have pre-done these ones, I would have, but as I said before, these need to be kept on ice for as much as possible. And the moment they're off ice, then you have some weird activity that's occurring that will change the results. You'll notice that I'm touching these with my hands. So make sure your students don't do that.
Just to let you know, the equilibrium is in the atrium, and the pizza is in the atrium.
Okay. So I have my 4 discs in here. And I'm going to now mix in some silver nitrate and hydrogen peroxide. Here's another question. So when students are doing this, they should be able to, ask the question and wonder if the volume of the hydrogen peroxide will change the activity. And if it does, suppose I use 5 mils of hydrogen peroxide. Will that make a difference? If I use 6 mils of hydrogen peroxide and add a mil of something else, it changes the concentration of peroxide from 3% to 2.75% or something like that. Will that make a difference? So those are questions they have to ask as they start modifying the environment. So what I'm going to do is I'm going to add 6 mils of this still. I'm going to add a few drops of this. I'd say a mil if I was doing it properly. And we'll see how that affects the experiment. Okay? So I'll pour that in. This being silver nitrate. So this is my silver nitrate experiment. A little bit of bubbles. So my students would have the graduated cylinder. They measure out 1 mil. They'd be wearing gloves. And when we're done with this, this is of course going to go into our waste bucket, not down the drain. Students know that. Okay. So I'm going to seal this up, twist. I hit the play button. I'm going to wait for 10 seconds. At the orange line happening now, you can see my screen, I hope. Almost there. Got a better grip this time, and I'm going to flip. Okay. So this is my silver nitrate. So looking at my silver nitrate, as expected, this is 4 discs. My 4-disc silver nitrate, take a look at it. Look at it. Compare it to the 4 discs, the purple line of just normal. Compare it to the blue line of 2 discs. My 4 discs, there's an initial reaction. How do you explain that? But then, look at the graph. If you can see it on the screen, I don't know how magnified or zoomed in you are, but if you take a look at it, at this point, is there any reaction occurring? If you take a look at that line, it's actually flat line. It's like sitting below 130. I can set up another screen that shows the digits, that shows the actual pressure. You'll see it's a flat line. There's no reaction happening here. There was an initial reaction, and maybe that peroxide hadn't reacted properly with silver nitrate, and maybe I need to spend more time mixing it. But at this point, even if there is a reaction, it's infinitesimal. It's minuscule. There's very little happening. So clearly, I'll let this run for 2 minutes just so you have a nice graph. Clearly, there's not much happening here. So this silver nitrate is having some impact on the function of this enzyme. So therefore, I might make the inference that the enzyme is being denatured by the silver nitrate. And if I ran the same experiment with copper 2 sulfate, I'd actually see a line that's higher than the orange. The copper 2 sulfate doesn't break down or denature the catalase as fast as the silver nitrate does, which is interesting. And so when we start looking at chemicals that we use for breaking down bacteria around wounds, we start looking at silver and its antibiotic properties, it leads to some really interesting conversations in the class with this, or questions you can ask on the lab for discussion and interpretation if you want to lead them in that direction. Okay, so we're almost at 2 minutes here, and I think I'm there. So I'm just going to take that off. Minimal air pressure coming up, and I'm going to stop. All right. So this is the experiment. So what does the probeware allow me to do? My probeware, it depends on how I want to take it. If you're in that era of science teaching where you don't want to do that big formal lab, then this could just be an exploration. You could do this to the demo at the front, better yet, get in the hands of your students, and just let them look at the graph. You don't want them to spend time creating the graph and doing a full-scale linear relationship, looking at the regression, looking at the line of best fit, sorry. Then you can get them just to look at the graph and then talk about what's happening here. And this will allow some really rich conversation in your class. So the last one I guess I can show you. I mean, how much time do we have? The last two I guess I can show you is like a pH difference. So I have a pH of 4, a pH of 7, and a pH of 10. So I can run the same experiment with those pHs, and it'll be interesting to see what happens. And when you run this experiment with a pH of 2, 4, 6, 8, 10, 12, you'll actually see a nice broad range. You'll see there's a peak at a particular pH, around 7, 9. And then the other ones, the 4s and the 10s, they show different activity, but they're not the same. Depending on the alkalinity or the acidity, you actually don't get the same as you get away from 7. And so that also leads to an interesting conversation around the tertiary bonding structure of proteins and whatnot. So I'll just do that one last one as a final farewell to our protein denaturation experiment. So let me wash this very quickly. Okay, washed, we're good. And I'm going to take my discs. This one. Remember, every single time I'm doing this, my discs also are my enzyme here. It's it's not as strong as it was before, but over a period, you're not going to lose that much activity. And it is on ice. I have very little here, so this amount of ice. Like I said, I'm just going to do 2 more here, just to show you a pH difference. Three. 4. I'm going to rest my bottle here. I'm going to get my peroxide. Fill it up. I'm going to use a pH of 10 for this one. And so when you're running this experiment, again, you have to decide, what do we run? Do we run 6 mils with 1 mil, 2 mils of pH of 10? You get the students to prepare beforehand and make sure that they're using the minimum amount possible so they don't affect the volume or affect the concentration. There's a lot of questions to be asked here. And if you're marking their lab design, those are the kind of things you'd be looking at. Okay? So I'm actually going to put my 6 mils in. But as soon as we'll design this lab, we're ready to decide how they're going to get a pH of 10. I'm going to add 1 mil of this, which I know from experience is enough to change the pH of the hydrogen peroxide. Put it off to the side. And seal it. Close it. I'm looking inside my reaction vessel, and I can see that one of my discs actually fell off the face into the liquid. So actually, okay. So this number here is going to be wrong. I'm going to run it because it just leads to some interesting observations. So take a look at that. So now I'm going to turn it and get them all reacting. So the moment a student sees something like that, I'm going to stop this shortly here. But the moment a student sees something like that, they should know there's something going on, right? It's like, hey, every other one started 100, that one started 160. Right? So have that conversation. Get them to think about the experiment. The results don't work out the way everything else has. It's likely something going on with the experiment. So I could tell when I looked at it, because I know to look for it, that my thing fell off. So I wouldn't have even run this in the first place, but they might not have. And I can immediately see that there's a problem. If I was doing the traditional gas technique with the gas being displaced in the gas collection tube, I probably would not have observed that. I probably would just like, oh, the pH of 10 is not producing as much as I thought it would, because a lot of the gas was already produced and escaping. So that's another little fail-safe that will allow them to, critically identify if they're doing the lab properly or not. So actually, I'm not going to do the pH of 4 and 10. I don't think I need to. What we can do, I guess we can post some samples from my students' previous experiments that show the pH range, and you can see what this graph would look like. I think it's a perfect time for any questions that might be out there. I don't know if there's any questions to be asked.
I'm not sure if can you see my channel?
I see. Thank you for your patience. So Rhonda said something, that was it.
Okay, so no questions so far. You want to? Yeah, no, so we're good. All right. Do you have anything else you want to add? Or?
I guess that's it. For this experiment, it's an enzyme catalysis lab. I run it annually. It's a 2-day lab that we run with our students. And depending on the semester, we change things up. But the probeware allows us to get some really rich analysis and allows us to go further than I could otherwise. If I stuck using just the gas collection tube and looking at the volumes of gas being produced, sometimes it's a very minor difference. So sometimes it's tedious for students to sit there over 5 minutes to notice a difference of 12 mils of gas being produced. Like no student really wants to do that, even though that's science. So this allows them to see very small differences among a pH of 7, a pH of 8, 0.1 molar versus a 0.2 molar or a 0.1 molar versus a 1 molar. It's a really amazing tool that we use in our classroom that actually leads to better learning. So it's not a toy or a flash, it actually leads to greater engagement and a much better understanding of the process. I guess that's it.
I guess the other advantage of the graph too is that students have a historical record. They have something representing the work they've done. Where if you're using the other technique, I suppose they're there for the experience. That's it. Whatever they read is fine, but they don't have a graph at the end of the day.
That makes sense. Yes.
True. Clayton, you did a fantastic job. Thank you very much. As I said, this is Clayton Ellis, and we're at David Suzuki Secondary School up in Brampton, just outside of the GTA. Just to clarify what technology he used from PASCO. He used the absolute pressure sensor. A lot of these are in schools. And if you want to make this wireless, it was the AirLink that he was using. It's the Bluetooth AirLink. It will work with whatever device computer you may be having, whether it's a PC, a Pack, a Mac, an iPad, a smartphone, or a Chromebook. So we'll work with all those devices. And it connects the same way as our new range of wireless sensors. This is a pressure sensor. So if you're interested in doing this experiment and you didn't have an absolute pressure sensor, you probably would just go straight to getting the wireless here, the wireless pressure sensor. They both connect the same way and would provide similar data as the one that Clayton used. So once again, Clayton, thank you very much. Tomorrow we'll probably have this recording posted online. If you want to get a refresher and you can't get enough of Clayton, you can always watch it as many times as you want. And we will have the data and some of the other materials that Clayton suggested. All right. Again, thank you very much for your time.